All right, I think we are a little bit late. So good afternoon, everyone. My name is Gaudi Bessos O'Connor. I am with NASA, and I'm on the program committee. And today's session is Progress Towards Sustainability. And this is the second session focused on electrified propulsion. Our first speaker is Colin Tschida from Wright Electric in the United States, and I'll have Colin ask to come and introduce himself. Did want to let you know that for this session, we will entertain questions after the speaker has spoken for approximately 20 minutes, so look forward to the conversation.
All right, well, apparently my mic is on. Thank you, Gaudi, for the introduction. As you said, my name is Colin Tschida. I represent Wright Electric. I lead the Powertrain program at Wright. And I've structured my talk today as just sort of an introduction to Wright's activities, as well as some of the ongoing work that we have. So with that said, it looks like those are my slides behind me. Maybe I'll reposition myself a little bit so I can see them. And I'll get started. So that's my name. This is my paper, my presentation. I don't think I need to repeat. I don't think I need to read it out loud because you can see it right there. So I'll go ahead and get started. If we could have the next slide. I do. OK, perfect. Which one do I need to use?
Whichever one you want. The one on the right, left has the pointer.
OK. Thank you. Thank you very much. All right. So my first slide here is something that you've seen a lot today, but I thought I would include it anyway. As we all know, there is a significant carbon footprint of flying. So the statistic that I picked up was that a single New York to Chicago flight is about 700 kilograms of CO2. Now, as was brought up earlier this morning during the talk, is that, of course, CO2 is not the only issue. There's also NOx, there's contrails, other issues as well to worry about. But the cleanest figure to look at right here is the CO2. So I went ahead and broke that out. And a New York to Chicago flight really isn't even that long, right? So we're all aware that short flights have relatively large CO2 impacts. But where is this emission created, right? Well, if we want to break it down, I'm sure many of you are aware that the lion's share of this emission comes from the wide body market. A small percentage comes from the regional sort of turboprop airplanes, but still a relatively significant chunk comes from the narrow body fleet, right? So unfortunately, if you look at this in terms of electrification or in terms of reducing carbon emissions, the biggest impact that you'd like to make is in the wide body fleet, but it's the hardest one to tackle. And the smallest impact that you can make is in the easiest one to tackle, which is in sort of turboprops, right? So where's a good place to start? Well, if you look at the narrow body fleet, it's a significant percentage of the overall emissions. It's visually that's say 40% or so, right? 45%. But not all those flights are equal, right? So if you tried to electrify a narrow-body aircraft to cover all of those flights, that's a significant challenge. But not all of those flights are the same. In fact, if we break that down further, and I didn't have the slide here, I thought I would just speak to it. About half of those flights end up being around an hour or so. There's a significant percentage of those narrow-body flights which are an hour or less. In other words, a quarter of the emissions come from narrow-body aircraft that fly relatively short routes. Right, and because they fly shorter routes, the energy storage demands are less, right, and therefore they become more addressable for electrification. So, is there a way to tackle this, and to tackle it relatively soon? So I thought I would just start with this. This is something that Wright is working towards. So the BA-146 is a four-engine up to 100-passenger airliner. It comes in a variety of sizes. And the thing to note here is that it's got 4 engines. So we're going to look at retrofitting a BA-146 with up to 100 seats. It's got 4 engines. And what can we do? Right, so I'll talk about that and the path that we're on to get there. Now, earlier this morning, we talked a lot about, or you heard a lot of people talk about zero emissions airplanes by 2050. This is great. I think that's a laudable goal, and it's the place we'd like to get to. But what can we do sooner? Is there something that we can do sooner? Is there something that we can do in 5 years, in 10 years that will have a significant impact? And wait until 2050 to have a zero emissions fleet, it's a ways, right? So how can we take these aircraft that are already flying, retrofit them, and make an impact soon? So the BA-146 provides a vehicle, pun intended, for us to get there, and I'll talk a little about how to do that. So the obvious thing is it's got 4 engines, so permits a stepwise approach, right? You've got 1 engines you can retrofit, 2 engines, all the way up to 4. Obviously, a 4-engine all-electric aircraft like this puts a real burden on the energy storage, right? But 1 engine places less of a burden. 2-engine places less of a burden, but displaces a significant amount of carbon. So as you electrify the aircraft, you can displace more and more emissions, right? While decreasing the burden on your energy storage system, and give you a path, give us a path to starting to reduce emissions sooner rather than later, right? It also conveniently, since it can fly, also conveniently, because you can retrofit 1 engine, and the BA-146 is certified in a 3-engine, is certified to fly with what's called a 3-engine ferry. You can do testing with 1 engine and start to test your powertrain in a way that permits sort of a relatively fast path to do so. So in other words, the stepwise approach provides a path for us to start testing relatively soon, and also provides a way for us to increase the degree of hybridization depending on the mission requirements and energy storage available. I'll speak to that more in a minute as well. So how are we getting there? Well, let me talk about the electric powertrain. I already mentioned energy storage, right? We're starting to spend time on energy storage. I'm saving that for a slide or so at the end. I'm going to speak most about our work on the inverter and the powertrain, the motor. So I'm sure, as all of you are well aware, the electric powertrain can be defined different ways. There was a lovely set of talks this morning about either parallel approach or a series approach. So this, what I'm showing here, is more of a series, right? So I'm showing a battery feeding the DC bus, going into the inverter, and then powering the motor, right? And it provides a relatively convenient way to retrofit. And this is the architecture I'll be speaking about. Well, Wright has benefited from a partnership with NASA through a couple of different programs, most recently a program called EAP. And we developed an inverter and 2-megawatt motor. So the pictures on the left there show the electric motor being tested in the lab. This is actually a facility at the FAA. We were fortunate enough to work with the FAA to do testing there. They recently installed a relatively large battery emulator, 700 kilowatts, which is a little bit small for our needs, but nonetheless a large battery emulator at the FAA for testing purposes. So it's really a great opportunity to work with them, and just an excellent opportunity to have done this in cooperation with NASA. So the motor, I said it's 2 megawatts. If you look at one of these, if you look at one of the fans on the BA-146, it's an ALF 502 or 507, handful of different variants, and each one of those fans generates is certified for 7,000 pounds of thrust at takeoff, depending on the variant and the airplane, and consumes, again, depending on the exact variant, about 5 megawatts, a little more, about 5 megawatts of power at takeoff. But at cruise, it doesn't consume 5 megawatts, obviously. It consumes about 2. So the 2-megawatt size motor provides us a way to start a little bit more manageably and test a reasonable flight condition. So this motor right here is really sized around the cruise conditions experienced by the ALF 502. So relevant flight conditions, not quite there for takeoff yet, but we're getting there, right? So this motor that you're seeing there, you're seeing one of our senior motor engineers, Earl, in that picture on the top left there, is, as I said, 2 megawatts. This particular motor is about 10 kilowatts per kilogram, and we're working on increasing that. What you see on the right is one of our first hardware builds for our inverter. This motor is sector wound, as you can see in the picture there. Let me see if I can do this. So you can see a variety of terminal boxes around the motor. This first motor, to keep things simple, we didn't bother integrating the inverters into the motor, so the terminal boxes provide a means to get the AC power from the inverters into the motor. And there's a variety of terminals around the motor. There's, in fact, 6, so there's 6 sectors. Allows us to have sort of a more manageably sized inverter, but also provides flexibility with the powertrain. So, you can have, for example, you can have more than one DC bus feeding the motor. So you could, for example, lose a DC bus but not lose the entire motor, right, by having multiple sectors in the motor. So baked into this topology that we have is some risk mitigation, and we're working towards having a platform which can tolerate some amount of failure and still provide meaningful thrust. On the top right there, what you're seeing is our second generation of 2 megawatt motor that we've conceptualized and working towards building. So this will be going to testing maybe starting next spring, and we're looking at doing propulsion testing as well as potentially also altitude testing at NASA NEAT. We've been working continuously with NASA, and they have excellent facilities, and we've been able to work with them to arrange access with them in the future. So propulsion testing as well as altitude testing of our motor and inverter. So eventually, this 2 megawatt powertrain, we're looking forward towards the end of next year or so, will be tested on a fan. So propulsion testing, and then optimistically, the end of next year, we hope to get this on an aircraft and start doing some flight testing as well. As you push the test campaign, we expect to find problems, and there's no way. There's nothing better than finding problems early so they can be addressed early, as opposed to waiting till later and finding them later. So all those 2 megawatt motors doesn't address yet the static power requirements. The topology is the same as our larger motor that we intend to fly. We're working on right now, and because of that, it permits us to start doing risk reduction early on in this program. I thought I'd speak briefly about powertrain development. So I mentioned continuous development. The motor that you saw there was 10 kilowatts per kilogram. And that's all in, so 10 kilowatts per kilogram for the motor, that's its mass. What I've got here is I've got a multi-objective optimization for the specific power and the efficiency of the motor, of this particular motor right here for the active materials. So the active materials for an electric motor, I don't know how many electric motor designers I've got in the audience here, but the active materials for an electric motor, like this one, it's a permanent magnet motor, so you've got the magnets, they're active. You've got the copper wire, that's active. And you've got the steel in the core, that's active. And everything else, the housing, the shaft, all that's passive. And a pretty good rule of thumb would be to say, for an aggressive motor design like this, maybe about the motor's going to about double, roughly speaking. So if I've got 20 kilowatts per kilogram of active material, the motor I'm going to end up with, if I'm good about my design, maybe it's going to be around 10, for argument's sake. So our first generation, speaking of which, was around 20 kilowatts per kilogram. We've been pushing the boundaries a little more with lessons learned through NASA, the testing that we've been able to do, and this development process. And our next generation motor, we're targeting more like 30 kilowatts per kilogram of active material. So our overall weight for the motor is going to be, a significant improvement, around 15 kilowatts per kilogram, around a 50% reduction. This comes from a couple of different. This comes from a couple of different levers. One of them is more rigorous optimization of the active materials, but also more rigorous optimization of the passive components as well. For our first build, one of my goals when this motor was designed was that I don't break it. I want to be able to learn from it, right? So there are certain things I did that added mass, but didn't add, let's say, value. The value they added was convenience. So, for example, this first motor had a solid shaft. There's no reason you put a solid shaft on an aircraft. It's wasted mass, right? Or the housing. You can optimize the housing thickness. But as we all know, as you start to push the boundaries of optimization, what happens is that it gets harder, right? There's more effort required to reduce mass. So we're we are starting to push those boundaries harder and working towards developing a powertrain which will be very aggressive, even more aggressive than what we have now, and meets our requirements. So, like I said, this is some work highlighting our sort of next generation development. Again, this is still at the couple megawatts. This is the one that we'll be testing in the near future, and really builds on this work that we've been able to do in cooperation with NASA. Beyond that, we're also working with the Department of Energy through ARPA-E. They have a program called the Ascend program, which there's a number of other organizations involved with that as well. They have really aggressive goals of 12 kilowatts per kilogram for the entire powertrain. This is for the motor, the inverter, the thermal management system, and this is really pushing people to the limit. So to address these, I would say, kind of the next generation requirements of the motor and inverter, we're working with a slightly smaller size to make it a little bit more approachable for us. But the topology is similar. We're working on these really in parallel, so that ultimately we'll be able to benefit from this program through ARPA-E, tied in with the work that we're currently doing, started through NASA, and we're going to end up with a very power dense package, right? So, the thing that I add here is I mentioned the motor. I briefly mentioned the inverter. I also mentioned here the thermal management system. This is shown there's a ram air. Oops. So there's a ram air style heat exchanger that's shown in the bottom there, and as been highlighted earlier, thermal management is a challenge, and what makes it a challenge, especially for electric motors, is the relatively low quality of the heat. We're not rejecting heat that's hundreds of degrees C. We're rejecting heat that is, 100 degrees C, right? So the size of the thermal management system obviously has to grow to accommodate the lower temperatures, required of the motor and power electronics. So designing those heat exchangers, making them meet mass requirements while not contributing excessively to the drag on the aircraft is a challenge, and it's one we're cognizant of and working towards in cooperation with ARPA as well as our own internal test campaigns. And then finally, I just wanted to mention a little bit about energy storage. So you've heard a lot today about hydrogen. It's sort of been, I would say, a significant theme of the talks around sustainable aviation. And I think the hydrogen economy is going to play a significant part in aviation. But there seems to be this sort of like either or. Like either we have batteries that are 200 kilowatts per kilogram that aren't good enough for civil aviation, or we have hydrogen, and there's no middle ground. And realistically speaking, there already is a middle ground, right? So one middle ground I've highlighted here is aluminum air batteries. It's something that Wright is looking into, and we're devoting resources of our own into pushing these chemistries. They've been around for quite a long time. They've been used by the military. Right now, there are aluminum air batteries with energy densities of about 500 watt-hours per kilogram, and reasonable sort of goals for aluminum air batteries can put them around 1,000 or maybe 1,200 watt-hours per kilogram for the pack. So with that comes some problems, right? There's no free lunch. So what do you get out of a 500 watt-hour per kilogram battery that you don't get out of a 250? Well, so let me level set a little bit expectations. To accomplish a 1-hour flight like we've talked about, and a 1-hour flight plus reserve, so you're going to have to divert potentially if there's an issue at your intended destination. You need around about 1,000 watt-hours per kilogram from your energy storage system. So clearly, the numbers that were thrown around in the talk this morning of 200, 250, it doesn't matter if it's 250 or if it's 200. That's not 1,000. So you're not going to displace your entire. You're not going to displace all of your jet fuel with batteries. It's just not going to happen. You're going to have a 15-minute flight. So what can you do? Well, first off, I'd say that obviously if 1,000 watt-hour per kilogram chemistry is possible, well, then there you are. You've got a solution, right? Comes with some potential drawbacks, but nonetheless, you've got a potential solution, right? So that's not yet demonstrated, something we're working on. But what can you do with 500? Well, 500 watt-hours per kilogram, if I recall from our presentation earlier this morning, was projected out around 2040, I think, for lithium-ion chemistries. But like I just said, a 500 watt-hour per kilogram in aluminum air batteries exists now. The difference is, though, is that it's a primary battery, right? So in other words, you use it once and then you've got to recycle it. The reaction of an aluminum air battery produces aluminum oxide, which then goes back, gets recycled into aluminum, and use it again. So it's an existing technology. It's been used it's been used by the military for quite a long time. Of all places, it's common in telephone exchanges in the U.S. as a reserve power system. So it's an existing technology. It has a lot of heritage. It's not been used in aerospace and has potential to grow. What do you do with 500 kilowatt-hour? What do you do with 500 watt-hour per kilogram battery? Well, just some basic math here. 1,000 watt-hours per kilogram may be necessary to displace all of the kerosene on your flight. With 500 watt-hours, that's about half of it, right? About half of 1,000. And it makes it accessible, just barely accessible, to hybridize a four-engine aircraft by about 50% over a 1-hour mission. So with near-term technology, hybridization is not that far away. I mean, you can't have a fully electric aircraft with technology that you pull out of your Tesla, but you can get, but you can start to get pretty close. And this is a goal that we're working towards. And as the technology matures, as we push the technology as an industry, we can start to maybe push that boundary of 1,000 and have an alternative to metal air or an alternative to hydrogen. There are also locations that are amenable to say this type of energy storage, which might not be amenable to hydrogen. For example, I was speaking recently with an operator that operates aircraft in Canada, and all of their not all of their, a lot of their flights are into remote communities without road access, right? So the way they operate is they truck in kerosene in the winter on ice roads. It sits there, and then during the rest of the year they fly in, they top off on kerosene, and they go. You can imagine you're not going to put a cryogenic hydrogen plant there, right? I mean, this is an extreme example, right? But it's an example of a place that isn't amenable to hydrogen infrastructure, and there are others as well. Small airports are going to have a harder time. Early on, at least, developing infrastructure for hydrogen. It'll be more achievable at large airports. So some solutions other than hydrogen are likely going to be a part of the mix. And like I said right here, aluminum air offers a path. It's offers a path in the near future, and it's something that we're digging into. So, in sum, I'd like to just maybe sort of discuss our timeline right here. Wright was started several years ago now in 2016 with the vision of electrifying air travel, a bit early, but nonetheless, our founder, Jeff Engler, started doing some of the groundwork, some of the research, figuring out what was going to be necessary. I joined Wright a couple years ago, which is when we really started our motor development program, and since then we've built and started testing our 2 megawatt powertrain and firming up our sort of goals and plans to develop the right spirit. So you see there, out in 2026, a little bit hard to see in that text. Easier for you. We have placed a date for first operation of a retrofit aircraft. So with that, that's all I would like to. That's all I have sort of structured, and I'm happy to take any questions that you might have. Gowdy?
All right. Thank you, Colin. We have time for a couple of questions. Mm-hmm. So if you have a question, we have a microphone. Please state your name, where you're from, and your question.
Yeah.
Thank you. Frederick from Saab. With the aluminum air battery, would you get a weight increase as it discharges? Have you accounted for that?
Yeah, you're right. So the Laminar battery, the increase in weight is about a quarter over over its discharge cycle. So a fully discharged Laminar battery increases weight by about a quarter or a third, depending on how it's operating. And what that does is it really limits, again, it limits your mission. So what I was trying to say earlier is with the 146, we can't replace the aircraft one-to-one, right? And I don't think that's true of any technology right now, right? But the question is, what flights can we start to address? What flights can we address soon using existing technologies? And so long as we have reasonable ambitions, right, and don't try and tackle a 2-hour flight or a 3-hour flight, by limiting the travel, by limiting the travel and having some degree of hybridization early on, we can tackle those requirements. Yeah.
Thank you.
But that's a good question.
All right, there's a question right here in the center. I think it's Susan. Oops, wait a minute.
Oh,
I think there's someone asking a question right here. 1 second, Susan. Go ahead, sir.
Is now more or less ready?
Yeah. So we've got a 2-megawatt motor in the lab. So the question was can you conclude from our timescale that we've got a 2-megawatt motor ready? And the answer is, let's say mostly yes, right? So we've got a 2-megawatt motor in the lab. It's again, it was built in collaboration with NASA, and this motor was built kind of fast and furious, right? We are making sure that we could that our overall topology was sort of sensible, that we could build the motor, that there were no showstoppers. So it's not a flight-ready motor, the one I've got in the lab right now. That's the one we're working on next. But it's a 2-megawatt powertrain. The topology, the cooling methodology, everything is the same as the one that we're building next right now. The main changes are sort of like for a motor designer, they're the incredibly significant but less exciting challenges. So cabling, right? Getting the right cables, getting the connectors, making sure that those peripheral systems don't have partial discharge. We've for those that aren't electrical engineers, one of the issues that you face as you increase altitude is that the onset of partial discharge the onset voltage for partial discharge decreases. So, right now, if you operate, a 1,000-volt system at altitude, you're going to get partial discharge, right? It needs to be isolated properly. It needs to have the right cabling, the right internal insulation. Yeah. But the motor is ready.
Okay.
Yeah.
So, Susan, I think you have the last question.
okay, thanks. Susan Ying from Ampere.
Hi.
And first of all, I want to congratulate you for your very impressive progress since when I first saw Wright Electric's presentation. I just have a quick question regarding the BA-146, which is basically a prototype here that you're going to demonstrate the technologies.
Yeah.
Are there any plans in terms of really retrofitting such an airplane for a product towards a product?
Well, so that's a great question. I think the best person to answer that question will be Jeff, but I'll take my our CEO, but I'll take my best shot at it here. So obviously the BA-146 is an aircraft that is no longer in production. Production ended, I believe, in 2002, and there's still not quite a couple hundred aircraft that are flying. Obviously of the newer variants, right? So Wright would consider it a success if we retrofit say 10 to 20 of those and fly those commercially on short routes. And the reason why I say that is because you don't really learn what the problems are until you start to operate the aircraft commercially, right? There are all kinds of things that need to get solved. One of the things that I didn't discuss here is logistics. It's going to be a huge challenge. It's a massive challenge for hydrogen, for batteries, for aluminum air. I mean, nobody should be dismissive about any of these challenges. If you went with lithium ion, right, you're going to have to, and you're going to recharge them. Well, you're going to have to pull in megawatts of power into an airport to recharge these things. I mean, it's a massive challenge. You need almost a nuclear plant next to the airport if you electrified all of the planes on the tarmac, right? Alternatively, for hydrogen, there's no free lunch there either. There's currently no infrastructure for piping hydrogen, for transporting cryogenic hydrogen, right? I mean, that's totally achievable. I'm not trying to say it's not, but it's nonetheless a real challenge. So you're seeing some creative solutions from people, for example, like universal hydrogen. I believe they were mentioned not by name but in passing earlier, and they proposed, for example, a system where you would bring hydrogen tanks onto an aircraft, right? Or you could talk about swapping batteries, and this is something that we talked about. So obviously with aluminum air batteries, you'd essentially be swapping packs, right? And the benefit of that is that the logistics become something sort of manageable, right? Because you can, if you start swapping things, that means you're bringing in things from other locations where you can either recharge them or mechanically recharge them or deal with them off-site. So there's less of a burden on airport infrastructure early on. And I think when we look out maybe 20 years from now to 2050 or something, that sort of burden on airport infrastructure is okay, right? This is something that we can tackle as a society before then, right? But if you want to start flying soon and have an impact soon, you can't expect that to be everywhere. So you need to have a solution that is going to be amenable to the current infrastructure.
All right, thank you so much, Colin.
Thank you, Gowdy.
All right. So our next speaker is Cedric Justin from the Georgia Institute of Technology. He is going to be talking about his regional air mobility market study. So Cedric. Go ahead. Oh.
Thank you for the introduction. So again, my name is Cedric Justin. I'm a research engineer at Georgia Tech. I do mostly research about regional air mobility and urban air mobility, looking at concepts of operation and things of that nature. So I think that's probably the clicker, if I'm not mistaken. Anyway, welcome to this presentation about regional air mobility market study. I would like to acknowledge my co-author, Professor Dimitri Mavris, as well as my sponsor, NASA and Gaudi, who have helped us sponsor this research. So if you have attended a couple of presentations today, you're probably sure by now that sustainability is a growing concern, and there is a growing awareness worldwide regarding man-induced climate change. It is unquestionable now that carbon emissions from human activities do contribute to the rising temperature worldwide. How aviation as a sector has been singled out as one of the main contributors, or at least one of the contributors to climate change. And for short-haul and regional aviation, this is an existential threat, because there is a threat of mode substitution over short distances. And we have seen in many countries in Europe proposition to actually ban regional and short-haul flying. However, regional and short-haul aviation have many benefits. We don't always speak of them. From an investment standpoint, there is unmatched flexibility in the presence of economic bursts and economic booms. If you build a high-speed railway line and the ridership is not there, you can't move it around. Aircraft are very movable assets. We have seen that during COVID. You can park them, you can move them to other markets. It's very flexible. And it's also a window to the world. As we like to say on the other side of the Atlantic, if you build a mile of highway, you can travel about a mile. If you build a mile of runway, you can basically fly anywhere. So speaking of infrastructure, this is a map that represents the aviation infrastructure in the United States. You have about 19,000 airports currently in operations. Out of those 19,000, about 5,000 are public airports. 4,000 of them have runways in excess of 3,000 feet, meaning that you could have regional or commuter services operating out of those. However, only about 520 are actually receiving commercial air services. So there is really a massive infrastructure that is underutilized. It's already paid by the taxpayer. It's used unevenly. There are some underutilized airports, and there is congestion at large hubs. And it is in this context that NASA's Electrified Powertrain Flight Demonstration Project conducts ground and flight tests of electrified aircraft propulsion technologies to enable a new generation of electric-powered aircraft. And why do I bring it there? Is because they're investigating 4 gauges of aircraft, namely a 19-pax aircraft, a 50-pax aircraft, a 100-pax aircraft, and a 150-pax aircraft. As part of this presentation today, I will be mostly discussing the 19-pax market segment. And why am I interested in this 19-pax market segment? Well, because it has disappeared. It has vanished from the US sky. Whether you're actually in Europe or in the US, you don't see many of those 19-seater aircraft around, and there are many reasons for that. First, it's a problem of public perception. People don't like propeller aircraft. They're noisy, they're rattling, they can't go over the weather, meaning they fly in turbulence. They're seen as old and noisy. And because they're old, they have also reliability issues. And because of those reliability issues, they also have poor economics. So I actually believe that we have a golden opportunity right now to change this public perception through the use of advanced technologies, whether that's more autonomy, whether that's electrified powertrain. After all, those airplanes electrified, they will be silent, they will be comfortable, they will be efficient, they will be green, supposedly. So the objective of this research is to understand whether state-of-the-art design with electrified powertrains can help re-energize a commuter or advanced regional air mobility market segment. So what is the advanced regional air mobility market segment? Well, it's advanced first, meaning that we have advanced technologies. We will have electric or electrified or hybridized powertrains. What about regional air mobility? Well, if I look at the topology of air transportation, we typically have twin aisle, we have single aisle, we have regional jet, we have commuter, we've got urban air mobility. Regional air mobility or commuter aviation is typically understood to be anything between 6 and 50 seats, flying short mission, typically not lasting more than 90 minutes, over short distances, typically less than 350 miles. And the focus of this presentation today will be on the market for those kind of operations. So we will be focused on the 19-pax seat gauge. We will be looking at business trip, because for those very short distances, leisure trip are not very common, I would say. And we will be looking at operating from some of those convenient yet underutilized airports that we have mentioned before. We're going to apply that to the United States. And we are going to split, actually, the United States in different regions. So we've got the Pacific Northwest, the Northeast Corridor, and so forth and so on. That's just to keep things manageable. We split it up into regions that have, according to socioeconomic connectivity, I would say. How are we going to do this market analysis? Well, first thing, bad news. There are no public forecasts for regional air mobility. Certainly not at the origin and destination market granularity that we're seeking, meaning telling us from where to where those aircraft, those people would want to fly. And certainly not accounting for new services from those convenient regional airports. If anything, there would be surveys with a status quo if we keep flying out of large airports and hubs. Fortunately, we are not completely out of luck. The Department of Transportation, Federal Highway Administration has released a traveler analysis framework which provides demand estimates at the county-to-county granularity in the US that project the demand for long-distance travel for each of those O&D markets, so county to county. And the demand is split according to purpose and mode, whether that's air, whether that's auto for business, auto for non-business, rail, or buses. And that has been empirically calibrated for 2008, and that also provides a forecast for 2040. How was it built? Well, it was built on a 4-step travel demand model. So what is a 4-step travel demand model? Well, as the name implies, you've got 4 steps. The first one is a trip generation. During the trip generation, we determine the number of travels that will be originating in a region, so in a county in this research. Then you've got trip distribution. So once we know how many trips will originate in a given county, we try to distribute them to other counties. How many people will be traveling between county A and county B? Then we have mode choice. What kind of transportation mode will people use to actually do those travel? And finally, you've got the route assignment, which is how people will actually get there. We're not very concerned about the later one. So how are we going to change or update this travel analysis framework to account for the availability of new services from those more convenient airports? Well, we're going to use this staff as a foundation, and we will keep the first 2 steps, meaning that the overall demand between any 2 counties is going to stay identical. We are not stimulating demand here. However, the mode choice is going to change, because hopefully if you have more convenient services from those more convenient airports, you will have more people flying. And this will be done, we will do that actually by creating passenger behavior models that capture the trade-off between travel time savings and expenditures when people are actually making decisions related to mode choice. We will calibrate that using the 2008 dataset of this travel analysis framework, and we will exercise it on the 2040 dataset to figure out how many people would be flying by 2040. Technical approach, it's a bit overwhelming, lots of boxes, I understand, but there's basically 2 things that I'd like us to remember. On the right part in green on the left part in green is what I would call the calibration exercise. That's when we will be calibrating the passenger model using the 2008 dataset. On the right side, you've got the projection. Once we have this calibrated model, that's when we predict how many people will be flying. In order to do that, you need a lot of inputs. So there are those black boxes at the top, and we will go over some of those black boxes that enable us to estimate airfares and travel times and so forth and so on. How are we going to do that? Well, we are going to use a generalized cost of travel. It's a well-established method, actually, to do travel demand projection. It's a sum of cash expenditure and value of travel times. The cash expenditure from riding an automobile for part of the journey, if you just go to the airport, or for the entire journey, if you just drive to your final destination, are going to be estimated using the US Internal Revenue Service's mileage reimbursement rate. The cash expenditure related to airfare and air travel are going to be computed using the DOT, Department of Transportation, BTS database. The driving time for the journey are going to be estimated using Bing Map API, and the air travel time, the block time of those flights, are going to be estimated using a regression from FlightAware. And if we use the 2008 dataset, we will be using a subset of airports that represent airports that had commercial services in 2008. If 2040, we will use a full set of airports. Airfare regression. So we use the Department of Transportation DB1B database, a market database from 2008. We look at the number of coupons to check airfare for both connecting and non-connecting services. We had about 11,000 observations, and we end up with this graph that plots airfare as a function of distance. Yes, it's not perfect. Obviously, distance is not the only explanatory variable in airfares. We've got time, how long ahead of the flight actually you purchase your airfare and many things of that nature. So it's noisy, which means that we would need to do uncertainty analysis later down the road, but that's the regression we got. For block time regression, we used data from FlightAware, retrieve flight time from aircraft that were operated in 2008, and we supplemented that with data from Cape Air, Mokulele, and the like. And that's the kind of regression that we have. Obviously, it's also quite noisy because we've got headwinds, tailwinds, and so forth and so on. But that's, I think, quite a fair middle ground here. Driving time, we will need driving time to and from airport, and we will need travel time from the origin to the destination. So we retrieve them from the Bing Map API. Here you have a categorized distribution that represent driving distance as a function of the direct distance. Obviously, it's distributed because you have sometimes some circuitous routing. Once we have that, we can estimate the door-to-door auto travel time, as well as the door-to-door travel time for air and ground non-stop services. So air and ground, because you drive to the airport, then you fly, then you drive. In red, you have the travel time for ground travel. In blue, you have it for air travel. What we see here is starting at 175 miles, you have this crossover point where you start seeing some real benefit of flying versus driving. For connecting services, obviously, you spend a bit more time at the airport. You've got circuitous routing, so flight time are a bit longer, and the crossover point is a bit further, about 300 miles. Once we have those driving time, flight time, and cost, we have everything to compute the generalized cost of travel. Now, how do I predict mode choice? Well, first we need to go through utility, and we assume here that the utility is a linear function of the general cost of travel with the constants alpha and beta, which are the ones that we will be calibrating. And once you have the utility of two modes, you can actually predict the mode choice using this logit model that provides you the probability of choosing air transportation in that case. So basically, as I said, we're going to use a 2008 dataset to do this calibration of alpha and beta constants. And what we do here, we compare the predicted value for air transportation from our model for year 2008, and we're going to compare that with the observed 2008 values of market share. And we use MLE, maximum likelihood estimator, to maximize the match between our predicted value and the observed value. And as you can see here, we have this sigmoid curve in blue, where in black you have our model, basically our prediction. In blue, that was the observed data. And we're basically matching pretty well the trends here. Obviously, there's some dispersion, and that's to be expected. Market models are never perfect. But any market where you have 0% market share, 100 market share are pretty well captured. If we look at the error, distribution of error, you would see that 80% of our prediction have less than 20% error, which is pretty nice, I think. Obviously, we can expand that to all of our markets. So we have here the Pacific Northwest, North Central, Midwest, Northeast Corridor, Southwest, South Central. And all of them are behaving roughly the same. Some are better than others. Usually what we see is that we have good performance overall. The trends are properly captured, and typically 80% of our market that we're looking at, so the county-to-county markets, have less than 20% market share, which is not too bad, I think. Now, looking at the Northeast Corridor, we look here at the outcome of this demand modeling exercise for air transportation. So we have those bivariate distribution for travel, where we have where we have at least 10 packs per day, at most 75 packs per day. We don't want to compete with a larger airline. And for distances between 50 and 350 miles. On the x-axis, you've got the demand in terms of passenger. On the y-axis, on the x-axis, you've got the direct distance. And the shade of blue represents how many market falls at the intersection of those two axes. What we see is that many markets exhibit low demand. That's to be expected. That's why we have those darker shades toward the bottom. And when we look at non-stop regional air mobility versus connecting regional air mobility services, what we see here is that we are basically losing quite a few markets that are on the low end, meaning on the shorter distances, just because connecting services over short distances is not very attractive when you can probably drive for the same amount of time. The next set of graph represents the air market preference as a function of door-to-door distance. So we have the market preference on the y-axis, door-to-door direct distance on the x-axis. The size of the marker represents the daily passenger demand. The color map represents the time savings. What we see as the distances increases, the air transportation mode choice start having a market share that approaches 100%, which is to be expected. The more interesting graph is the one to the right, which basically is the switching rate, which is a percentage of travelers expected to drive for business purposes in the original TAF survey, but that ended up choosing air transportation once those new convenience services were introduced. And you can see that the switching rate is quite low for those shorter distance, that's to be expected again, and is quite high, typically 100% towards those longer distances. Now, we have seen over the different market regions that there is demand, actually, for regional air mobility. The demand is there. We were able to show that, and that was shown for the Northeast Corridor. In the paper, you can see that you can find it for those other regions in the US. The next question is, can the passenger demand for regional air mobility service be profitably served? It's fine to have demand, but if you fly from Grand Rapids to Kalamazoo and your aircraft is sitting on the ground because there are no further service beyond Kalamazoo, then you're probably not very profitable because your aircraft is sitting on the ground and an aircraft on the ground is not generating any money. So we developed first an economic model to estimate direct and indirect operating costs for the 19-seat EPFD vehicle. And we use a regional air mobility demand estimate that we just presented to generate an operating model by optimizing flight schedule and fleet assignment to maximize operating profits. And the optimization is formulated using a novel in-house, we created it, MIP linear program formulation that was solved using the GURU-B optimizer. On the right, you can see basically a depiction of the market. So before any operation modeling is done, that's basically where we start. This is the demand that we have on all those county pairs. And below, you have it aggregated by airports, all the passenger originating at a given airport. Unsurprisingly, you see the typical big hitter in New York, Washington, Baltimore, Philadelphia, and the like. This is the outcome of the optimization. Once the scheduling and fleet assignment was done, now fleet assignment, we've got a single vehicle, so it's just going to be a 19-pax aircraft anyway. But that's basically the set of routes that we could profitably fly. And on the right, you see basically the airport that we would be flying to, where the bubble represents the size or the demand that we have originating at those airports, and the color of the bubble represents the amount, the fraction of the demand that is actually served. So the lighter the color towards the white, meaning that we actually serve most of the demand at that airport. And you can see that many of those bubbles have a blue shade that is quite light, meaning that we serve probably 60–70% of the demand originating at those airports. Couple of metrics, some of them are not that interesting for this presentation, but again, those are profitable operations. Here, 1.4 million operating profit per day. 148 airports served out of the 202 that we are considering for this part of the US. So that's plus 68 airports versus what was commercially served in 2021 or 2020 before COVID hit. 1,095 different markets served. But for the market analysis, what's most important is the number of 19 aircraft that we would need, 648. That seems large. It seems large to me, especially given that Cessnas and the like are not selling that many aircraft. But keep in mind that in the New England area, so basically in the top right corner of this Northeast Corridor, we have Cape Air that is operating a fleet of about 100 aircraft. So you quadruple about the size of the area, and you multiply by 5 the fleet of Cape Air, which is about 100 aircraft. So that's in line, I would say. Obviously, we can do that for those other regions, so Pacific Northwest, North Central, Midwest, Northeast Corridor, Southwest, South Central, and we kind of show some similar trends where we do have a market for 19 pax vehicle. Now, the last question that I would like to answer is what happened when other competing aircraft gauge are introduced? Right now, we just introduced a 19 pax aircraft. What about if we introduce a 9 pax aircraft or a 30 pax aircraft and the like? Meaning we have competition among the aircraft. So the first one we introduce is a 9 pax aircraft, which is based on the Tecnam P2012 aircraft. And it's fully electrified, meaning that its range is going to be limited just because it's fully electric. The battery technology is what it is. So we have 150 nautical mile of range. So it's just going to be able to fly some of those shorter routes. We have the 19 pax aircraft, which is basically the PFD baseline. And we bracket from the other side by an umbrella-like aircraft, a 30-seat aircraft, which is using a hybridized powertrain, like the 19 pax aircraft, power boost with a design range of about 330 miles. Let's see what happens once we put everything in the flight scheduling and fleet allocation solver. That's what we get. To the left, we've got the 9-seat network, so those flights operating by 9-seater aircraft, middle for the 19-seater, and to the right for the 30-seater aircraft. It's pretty apparent that the 9-seater aircraft is quite popular, I would say. Profits are a bit higher, 1.5 million, but that's not really what I'm concerned about here. Number of airports served, 156 airports, so plus 76 versus 2021. That's good news. Obviously, we have a smaller gauge aircraft, so we can reach some markets that have lower demand. That's the beauty of it. Let's now look at the fleet size. 9-seat, we have 489 aircraft in that case. 19 seats, 146. 36, just 47. Remember, before we had 600 or so 19-seater aircraft. So basically what it means is that the 19-seater market has been displaced by the 9-seater aircraft. So the 19-seat aircraft gauge is displaced by the 9-seat aircraft gauge owing to less competitive economics. The reasons are pretty well understood, I would say. We have, beyond 9 pax, we have more stringent regulations. We need two flight crews. We have 2 flight crews. We no longer have Part 135 operation. We need to go to Part 121 operation. It's just more expensive, and that shows here. Which means that the 19-seat gauge might not be actually the optimum gauge to serve a regional air mobility service. Maybe we need something smaller. And in addition, when you have something smaller, and let's say you've got less demand, you can actually fill a 9-seater aircraft with 6 pax and be profitable, whereas a 19 pax with 6 passengers on board is probably not very profitable. Conclusion. So all in all, we have developed a parametric regional air mobility demand model, which is accounting for varying geodensity of airports to support regional air mobility services. We also account for the attractiveness of non-stop versus connecting itineraries. Did not speak too much about that, but we have less demand for connecting services versus non-stop services. We developed a mixed integer programming approach, optimization, to solve the integrated flight scheduling and assignment that allows to assess profitability and extent of operation, and that provide estimates of market size for various aircraft gauges. And finally, we found out that there is significant passenger demand for regional air mobility services. We have a sizable market for the 19 pax aircraft in isolation, but when we bring on competing aircraft gauges, namely the 9-seater and the 30-seater aircraft seat gauges, the 19-seater aircraft market is actually captured by the 9 pax aircraft market, just because the 9 pax is more economically efficient than the 19 pax. All right, that basically concludes my presentation, and I thank you for having listened to it.
Thank you, Cedric, and we can take a few questions. So we have the microphone. Please raise your hand. Okay. Great job.
Christopher Journet, Saab Aeronautics. Thanks for your presentation, Cedric. I got one question. Have you done any sensitivity analysis on technology levels and battery levels?
Yes, we did actually. We did some sensitivity. I did not present that for the sake of time. We did some sensitivity analysis on the battery technologies, looking at various specific energy densities and seeing how that affect mostly the range of the 9-seater aircraft. And what the outcome of the sensitivity analysis was is, as you increase the energy density of the battery aboard the fully electric 9-pax aircraft, its range increases accordingly, and basically it captures more and more of the 19-pax market, to a point where I think when you reach 400 watt-hour per kilogram, which is pretty sporty, I do understand that, the 19-pax market completely vanishes again, and we only see 9-pax aircraft. So yes, we did that. We also did some sensitivity study on the number of flight crews you would need aboard the 19-pax aircraft. You know, if regulation were to change and you could go from 2-pilot operation to single-pilot operation at 19-pax, and that does help a bit with those simplified vehicle operation.
Okay, there's a question all the way far left, or far right.
Thank you. Hello, Cedric. Got a question regarding I've got a question regarding carbon emissions. So on those slides, you gave the kilogram CO2 per mile, I believe.
Yeah.
And or per passenger mile, I think. And I was just curious, since you're stimulating demand essentially with air travel, how does that compare with the car travel you're replacing? Have you done that analysis as well? I don't actually know. I'm just curious how it pans out.
Yes, we did. It's not part of this paper. We have done that in previous study, where we actually compare the carbon emission per seat per pax with other modes of transportation. Obviously, it's a bit worse than cars, and it depends on the load factor on your car. You know, whether you're traveling alone, which is what most of the people do in their car, versus whether you've got 4 people on board the car, because obviously aircraft are typically packed. But yes, we looked into that, and we also looked into doing the optimization, not only to maximize profit, as I showed today, but also to maximize profit, a kind of a hierarchical optimization, where we first tried to optimize profit, and then we let those profits be degraded by up to 10% in order to decrease carbon emissions. The end result was basically you're shifting a little bit of the 19-pax market, which is a hybrid electric aircraft, so it still burns some fuel, to the 9-pax aircraft, which is a fully electric aircraft. And to the point where at the end the 19-pax aircraft is really only serving routes or markets that are beyond the range of the 9-pax aircraft. Yeah, but it's quite competitive, yeah.
All right.
Yeah, Susan?
Well, I have one comment and one question. So comment first. This is a fantastic study, better than any of those McKinsey's market study that I have seen so far.
Thank you.
But don't go to McKinsey's. Stay in Georgia Tech. The question has to do with the pattern of the routes. It's very interesting that when you introduce the 9-seat and 30 seats, it makes change of the 19-seat market. So my question is, have you looked into just how this could really change? Because currently the airlines, they arrange their fleet by hubs and spokes type of strategy. Have you seen if this can really lead to the true point-to-point kind of on-demand travel?
Yes, so that's a very interesting question, as a matter of fact. I would say 2 elements of response. First thing is, in the network that we were showing, I don't know if I can go back, no I can't, about 60% of the people were actually transported on non-stop services. All right, so that's one thing. And second thing, regarding hub and spoke, we did set up some connecting hub for those regional air mobility services, because we understand that when you have 11 packs per day, it's hard to justify having 3 or 4 frequencies, but frequency is king for short-haul services. So we do have those hubs where we can aggregate the demand so that we offer more services, but we purposefully set them up in airports that are large enough but not major hubs, because we don't want to have hordes of 9-seater aircraft swamp Boston or JFK Airport. A big airline won't be very happy with that.
All right, I think this is great. Thank you so much, Cedric.
Thank you.
Okay. So the next paper is an update on the subsonic single aft engine called the Susan Electrofan Trade Space Exploration, and is from my colleague Ralph Jansen. And Ralph was unable to come today, so you have the pleasure of me briefing the presentation charts, and hopefully I'll be able to do it justice. So be gentle with the questions. I'm an experimental aerodynamicist by training, so I'm earning my merit badge with respect to electrified powertrain systems. So the Susan Electrofan presentation, oh shoot. Is there any way you can put the chart over there? Because I hate talking down. I'd rather talk to the front. Yes, no? Probably? Okay, we'll just try to do the best we can. So so this work is a trade study on what could we do if we had a clean sheet of paper, and we're looking at the narrow body for regional mobility. We feel that that's really the trade space where such a vehicle could take maximum effectiveness for electrified powertrain systems. And this work is done internal to NASA. So if any of you were here for the Saab presentation last night before the students had their mentoring session, they had something called the Rainforest Project, which was internal innovation. So NASA has a group of folks that do sort of the same thing. It's run through the project called Convergent Aerospace Solutions. It's called CAS. And so this is what it's called, the CAS project within the NASA Aeronautics Mission Directorate. And so the individuals are all a variety of subject matter experts, both in the airframe and the electrified powertrain trade space. And so they've put together what they think would be an appropriate configuration to assess. So I think I've basically done this. One of the things that we did is that upfront constraint is that we were going to fly this airplane within the current infrastructure, both from an airline operations and a ground infrastructure. So no new systems would need to be developed for this from a operational perspective. So I guess the key thing here is the Susan concept is looking at accelerating two S-curves simultaneously. They see the value in a distributed electrified powertrain distribution system architecture, as well as taking advantage of the alternative fuels effort, the sustainable fuels replacement, drop-in fuels, all the way up to, zero carbon fuels. So the architecture you're going to see actually enables both of these S-curves innovations to grow and mature, and they could then be included in the trade space. This is an interim status, so I'm going to show you a few preliminary results, as well as show you the future work that's going to be done by the team. So I'm not going to talk this anymore. We all know why this is really the market, the sweet spot for this type of aircraft, narrow-body aircraft, the passenger fleet. I think the key thing to share with you is that the aircraft is targeted for a design range of 2,500 nautical miles, but the economic range is 750. And there is plenty of forecast data showing that if we can target that economic range of 750 nautical miles, that is the sweet spot from an operations perspective. Okay, so this is the chart I just talked about. So you'll see that this is the mission profile that enables the 750 nautical mile economic mission. And one of the things that they have done is they addressed if we were to lose the turbofan. So this actually will have 16 propulsors on the wing, 8 on each side, and a turbofan in the aft section of the tail cone. And if the turbofan were to fail, there is a two battery systems, rechargeable battery systems for the propulsors, and a one charge battery system as a backup if the turbofan were to fail, and that would provide enough thrust to operate 60% of the propulsors so that it would get us back home. So they were very worried to make sure that they could meet the FAA regulations for engine out condition. All right, and so but this architecture will then enable them to fly under the distributed electric propulsors 300 nautical miles for about 30 minutes at Mach 0.785. So that's kind of the map of the US. It could basically land wherever it needed to if there was this emergency situation, if the turbofan were to fail. Okay, so the distributed propulsion is the concept that they're looking at. They're looking at having 8 on each side. They're planning to embed them into the lower surface of the wing to enable taking advantage of the pressure ratio, taking advantage of the aerodynamics. The design of the fan pressure ratios is each propulsor would have nominally 1.35 fan pressure ratio. The trades will include assessing aerodynamic drag, considering the graded wetted area and the cross-sectional area for the system. And they recognize that there is a weight increase with having 16 propulsors in this architecture, and they're hoping to be able to minimize that weight by introducing other aerodynamic features such as natural laminar flow to help provide offset the drag penalty. So here's natural laminar flow. This is one of the technologies that NASA has been developing. It's called cross-flow attenuated natural laminar flow, and basically it takes advantage of the transition front, which is the far pink. Oh, wait a minute, go back. Where's my little, no. It takes advantage of maintaining laminar flow. Approximately 53% natural laminar flow can be maintained using this technique, and you use passive aeroelastic tailoring of the actual composite wing to make this happen. Okay, the turbofan engine has the traditional architecture that you see in a turbofan. I'm not thinking that there's anything really different. They have completed a low fidelity assessment of the power split between the low spool and the high spool. They have identified how they would actually, oops, I am so sorry. They have identified how they would split the megawatt power between top of climb and rolling takeoff. And I'm not going to talk the details, but you can read the paper. It's really well thought out and explains the approach for doing this. And this is the electric engines. There's 16 identical electric wing-mounted fans. They're basically a ducted fan architecture that provides, it's a dual counter-rotating fan design. And it gives you, well, I thought it was 1.35. It's 1.25 fan pressure ratio. And so one of the things that they are looking at is also taking advantage of boundary layer, both on the wing as well as in the tail cone area of the aircraft. And so this is the actual power system, very complicated diagram. I'm thinking that we have 20 megawatt power is what it will generate. It has 4 5 megawatt main generators, and each of them has their electrical systems. We also have, I'm not even going to try to go through all this, so I apologize. The single use battery, which is for the turbofan failure condition, allows for 30 minutes of flight. The power system does enable the aerodynamic propulsive benefits of the targeted Susan architecture. The thermal system, it's one of the biggest barriers across all of electrified powertrain architectures. And one of the things that they're trying to do is really look at how to leverage the secondary subsystems and integrating them with thermal management system, so reducing weight. This means taking advantage of incorporation into the structure of the skin, the EMI shielding architecture, and the fuel heating in cold environments. And so there's various options that they're looking at with respect to the thermal system configuration. And thermal management is an issue that we're also addressing within the EPFD project on our flight aircraft test demonstration. So there's learnings that are going to be shared between the actual flight demonstration project and this trade study team. So electric taxi is one of the key performance features of the Susan airplane. They're looking at being able to reduce the fuel burn expenditure of approximately 6% for short-haul fleet operations. If we can use the Susan architecture that will allow the use of the existing onboard battery power to perform all or a portion of the taxi maneuvers, that will be, that is a huge benefit to this architecture. So thrust-based flight control is how they're planning to maximize the efficiency of the DEP, and they are working on expanding the bandwidth of the hybrid electric engine to be more responsive for the turbofan response time and allow for increased effectiveness of the flight control system for the Susan aircraft. They're in the process of actually developing the flight dynamics models and the flight control laws for the simulation. So I am probably just gonna, overall the technique or is the building of, oh, shoot, sorry. Go back. Okay, so the control laws are being built based on the turbine electrified energy management system algorithms that leverages the electronic power system, notably the machines, the energy storage, and the interface between the turbo machinery. And the goal is to selectively modify the operations of the engines by transferring power from the low spool to the high spool as appropriate across the mission. Let's see. Too many words. You guys can read this at your leisure. So we also have the flight deck. So the Susan flight deck is being designed for a 2-flight crew operations, and the thrust of the airplane will be highly optimized for the engine control system and therefore the flight crew will not need to, need differential throttle control. However, the flight crew will have the ability to manually shut down any of the 17 engines. They are going to be doing human-in-the-loop studies to explore the need for multiple throttle handles in nominal and off-nominal conditions. So conclusions and next steps. So NASA is conducting the ongoing trade study on how to utilize the 20-megawatt class electrified aircraft, leveraging the latest technologies, and anticipates that the next study upgrade will enable a finer look at the configuration and the combination of technologies to yield significant fuel burn and emissions benefits. And another thing is we're also going to look at the key goal to reduce costs per passenger mile. And I did want to just summarize the key attributes from the requirements perspective so that you guys can see that the initial study showed that this configuration achieved 17.2 to 26.8% fuel burn reduction, and also a reduction in the cost per mile. Through the I'm sorry, I did want to check one more thing. It said, through the ability to transfer power between the low spool and the high spool, they're not going to need a bleed air system, and so that has reduced the fuel. That has resulted in a 1 to 2% fuel burn benefit, and the e-taxi mode will enable 6% of the current fuel expenditures for short-haul fleets. So that is Ralph's presentation. I hope that next time that Ralph can come here in person and share with us the results of his architecture and where we are with the trade study. So thank you, and I'll try to answer a question or two if I can. If there aren't any, well, you're going to put me on the spot.
Okay, thank you for stepping in and giving this presentation. It's very interesting. My question, it's a concept, but is it planned to realize this concept by a demonstrator or something which is really flying? Because the approach is relatively innovative.
So NASA doesn't build airplanes as a business. We explore the trade space and we do demonstrations where we feel that there is a high payoff, high risk technology that needs to be matured to flight. And so the Electrified Powertrain Flight Demonstration Project, which is the one that we spoke of 2 days ago, Monday's session in the afternoon, talked about we're doing a initial powertrain system with 2 industry partners. And so this is to gain knowledge on how to actually make electrified powertrains operational. We'll take those learnings from those 2 flight demonstrations to help inform how better to do an architecture that really is for a single aisle, because our flight demonstrations are not being done on single aisles. They're done on turboprops because the technology is not there. We anticipate that this technology, these trade studies will help inform what are the next demonstrations that need to happen in partnership with industry. So we don't anticipate building such a demonstrator. We're learning improving our physics-based models through flight demonstrations of much smaller scale to help inform how do we actually develop an architecture that works. And we're working with industry to validate these architecture studies.
Okay, thank you.
Okay. I think I'm going, oh, one more?
Yeah, one more question, please. So my name is Daniel Kerbel from Airbus R&T. You need to look on your right. There
Yes.
I am. Yeah. So you started to answer the question I have, by the way. Just 2 questions. So first, you mentioned a fuel burn improvement. It was versus which reference?
The fuel burn improvement of 17 to 26% was based on the initial architecture that included the distributed electric propulsors as well as BLI plus natural laminar flow wings. So it's a technology suite. It's almost like a technology collector is how we do our systems analysis assessments. And so it's putting those and then looking at how we actually operate the electrified powertrain system with the turbofan together enabled that fuel burn prediction.
Okay, so you are talking about NLF. I imagine it's possible to put NLF because you have your distributed electrical propulsion.
Yes, yes, that is an area of concern because we understand that NLF doesn't like disruptive flow. And the propulsors will have an impact. So one of the things that our researchers are looking at is actually embedding the propulsors on the lower wing sections to help minimize the disruption of the flow over the leading edge of the wing. And through passive aeroelastic tailoring of the wing shape, we'll be able to harness the energy to maintain laminar flow. And the computational codes are showing us that you can achieve CAT NLF using cross-flow attenuation technique of about 53%. But this is an area that we still need to research more. We probably would need to go into the wind tunnel to validate the CFD to see if it's really feasible to have an embedded distributed propulsor system as well as a wing shape that was tailored to enable natural laminar flow.
Yes,
So
because at the end you have a quite low sweep angle.
yes.
And then your the positioning of your distributed electrical propulsion is on the aft under intrados.
Yes.
Correct. Okay.
Yes. Yeah, it is a challenge area. We recognize that.
And last question. So maybe you started to answer that one. I have understood that, if I have well understood, sorry, you were forcing to perform a kind of scaled flight demonstrator with this approach or not?
So at this time, NASA does not have plans to have a scaled demonstrator. What I was trying to share was that we are doing an initial electrified powertrain demonstration with industry. We have 2 industry partners, but this demonstration is being done on a turboprop aircraft, a Saab 340 and a Dash 7. And the Saab is with GE Aviation, and the Dash 7 is with Magni-X. We anticipate that the learnings from these demonstrations, these flight demonstrations where we're going to get experimental data, will help inform how we actually want future architectures to work to enable a regional narrow body.
Thank you.
Okay. One more, Susan.
Yeah, well, I have to comment on the fact that this acronym is just brilliant. Actually, my first question is very similar to that gentleman just now from Airbus. It is, the fuel reduction baseline, because 17 to 28% comparing to, and my original thought was comparing to the baseline of something like a 737.
It is a 737
Okay.
2005.
Okay.
It's based off of that. I'm sorry, I forgot to mention that it's based from that initial 2005 reference. It's the standard reference that NASA uses for all of its fuel burn calculations.
Yeah, and I think that's just wonderful, but I think we can do better, especially seeing those electro jets that are in the back of the sort of profile airfoil. And I was wondering if there's a particular implementation on the flaps, because they're towards the back for the whole wing, right? Or not the whole wing, the inboard part.
Right.
So that's particularly over the flaps, and so the circulation, particularly using the jets, that's going to really help your high lift tremendously. And I think the reduction of fuel will be much higher than what you can calculate at this point.
That's a really good point, and we haven't optimized the wing. We're still in the first, second iteration on how to optimize the system. Now that we understand, we're learning how to model this very complicated airflow over the wing with the propulsors and natural laminar flow, and the other, as you said, the flap system.
Yeah, and I think in addition to a demonstrator that's working together with the industry and so on, from the simulation part, because there are a lot of very powerful simulation tools from the industry that we should be able to work together as well.
Okay, look forward to that. All right, thank you. With this, I would like to transition to our next speaker. Really appreciate the questions and your patience. Okay, so the next speaker is, oh my gosh, I just lost you, Michael. I'm so sorry. Why don't I just hand it over to you? Michael is from the European Union, and he will be presenting his presentation. Here you go. Use this one.
Thank you. Hello, good afternoon. So my name is Michail Kyriakopoulos. I work for the European Commission in Brussels from DG Research and Innovation and in the group of aviation. And in the beginning, first of all, thank you for the invitation. In the beginning, I thought that I'm going to select 5 different projects, representative projects in aviation, to link them with climate neutrality. But soon I realized that there are far too many projects being presented here in ICAS. So I switched to a more standard presentation to give you an overview. But first things first, you have best regards, greetings from Director of Energy and Transport, we call it Clean Planet, Rosalinda van der Vlies. And the head of unit responsible for aviation, Jean Lamila. You know, over the last 35 years, where the European Aviation Research Program is active, since FP2, and my dear friend and colleague is standing here in the first row, remembers very well, more or less we have been following a kind of priorities based on these three documents and the predecessor of these documents. The first was the ACARE one, the second is the IMG4, the industrial strategy, and the area agenda in different formats. But all these things more or less have kind of changed recently. I mean, I recall back in 2019, we using this kind of slides, where the drivers of aviation were based on demographic changes, on emerging countries, megacities, air traffic doubles every 15 years, high demand, production ramp-ups and rates, unacceptable delays, and so on and so forth. But that is very distant right now. Our vocabulary, also in the European Commission, but also throughout the world, has changed completely just over the last years. And that's how it looks like, more or less, in 2022. People were very active, not because it was COVID, but because there were fundamental changes. Everybody speaks about climate neutrality, and there are many here that spoke before me. And of course, we have the new ACARE Green Deal strategy. We have the DLR, zero emission. We have the Destination 2050, the waypoint from ATAG. We have Future Skies from World Economic Forum. We have the French ONERA Strategic Research Agenda, the Fly Zero from UK. We have the AREA, Future of Aviation. We have far too many strategies right now, and all these point out the very same thing. Point out the new kind of world order, which is since very recently, since 190-something days, also occupies our mind. It's about energy security, new geopolitics, climate neutrality, global economy, increased uncertainties, inflationary pressures and localism, non-fossil-based fuels for aviation, more sustainable aviation fuels, very ambitious targets, hydrogen electrification, impact of non-CO2 emissions, and of course post-COVID recovery and readiness for new pandemics. So, of course, we speak about climate neutrality. We don't speak about decarbonization in the Commission. We speak about climate neutrality because we want to include, from now, we know quite well over the last 25 years, with the help of DLR and many others that we worked with them, that the impact of non-CO2 emissions is important. That's why we don't have in our vocabulary the word decarbonization, but we have climate neutrality. And but put numbers aside, I want to make this point here that aviation can offer a bit more than we're used to think. Global anthropogenic CO2 emissions, with reference of 2017, are approximately 37 gigatons. So global aviation was a kind of 0.8 gigaton, 859 megatons. And European aviation, 171. And the last line is 8 gigatons. That was the impact of global forest fires back in 2017. So the point I want to make here is that aviation and the benefits of aviation go beyond traveling and, of course, search and rescue operations, stuff like this, but also we can make a big difference to fight global forest fires. And as I said earlier, we go beyond CO2 emissions. In the European Union Aviation Research Program, we focus also beyond technologies, also on aviation noise, local air quality, and of course the impact of non-CO2 emissions. And I borrowed here the slide from the FP7 project, React4C, that is approximately 8-9 years ago back. This slide where shows the impact of non-CO2 emissions with respect to the flight attitude and contrail formation. Undoubtedly, over the last period, a lot of good work has been done, and I want to and we spent quite a lot of time reading very carefully the report, the ICAO-CAP Long-Term Aspirational Goal Task Group that was published in March 2022, and all the good work that was done there. And it shows clearly that we all recognize the climate impact of aviation, and something has to be done more than words. That was more or less the case in previous decades. This slide, you will find it in the Clean Aviation Strategic Research Innovation Agenda, and it shows quite clearly the path that Europe is planning for the years to come until 2030 and beyond. And you can see here new aircraft architectures. You see here the different, let's say, from system verification to full-scale integration and ground testing, and all the way to 2030 introduction, service, and beyond. And all this goes and links together with a bigger program that we have in the European Union. We call it the European Green Deal. It's a package of measures, regulatory and non-regulatory, that they have been allocated a huge amount of money. 1/3 of the 1.8 trillion euro budget of the Union will go to the European Green Deal. So how these things are implemented? As I said earlier, in the Commission, we have framework programs. That's kind of 7-year programs. And right now, we call it Horizon Europe. It's a budget of approximately 100 billion, 95.5 billion euro from 2021 to 2027. The purple there shows the global challenges and European industrial competitiveness, and that's where also the budget of aviation is coming from. Bird's eye view for those that have not, because here's a kind of international audience. If it was a European audience, many Europeans know this kind of better, but I found the opportunity also to present this in a more international audience. Excluding the first column, we have 3 pillars. The first one, pillar 1, is about excellent science. It's all about the very fundamental research and science. It's about scholarships and fellowships. We call them Marie Curie. The second pillar is about global competitiveness and the industrial global challenges and industrial competitiveness. And the third one is about pillar 3, more on small and medium enterprises and more close to the market uptake. So all aviation programs, literally, they are coming from Cluster 4 and Cluster 5. Cluster 4 is approximately 15 billion, and Cluster more or less the same, Cluster 4 and Cluster 5 the same. So how this is structured? In Horizon Europe, we have so-called, beyond the collaborative program, we have the so-called partnerships, more than 49 partnerships. I highlight in red the ones mostly relevant to aviation, but many others. For example, like photonics, made in Europe, artificial intelligence and data robotics, all high-performance computing will all also give synergies with the 3 main ones, which is, of course, clean aviation, by far the most important one. CESAR, which is the air traffic management, and the clean hydrogen one. So these 49 partnerships are industrially led. They do a work program on their own. Starting point, the industrial needs. Of course, they have to albeit, they have to focus all the political orientations that we have in the European Union. And that's what has been done over the last 2 years. Here you see the covers of the Clean Aviation Partnership, the Clean Hydrogen Partnership, and the Digital European Sky, traffic management, that all these give rise to work programs where scientists from all over Europe and all over the world can apply for contracts. First things first, as I said before, the most important one for us, the Clean Aviation Partnership, and with a budget of 1.7 billion from Horizon Europe, from this cluster, from this Pillar 2. And the first call was launched the 23rd of March. Deadline is finished. All projects have been evaluated, and the results are going to become soon public. They have been allocated 14 topics, 736 million euro. I'm not going to go read all of them. These are the 14 topics and how many number of projects we expect and how much value is associated to each topic. In a similar fashion, also for clean hydrogen, and here we have also topics under the Clean Hydrogen Partnership that are responding to aviation, and the first deadline was 180 million, 120 on the second one, 300 million for the first batch in the work plan 2022. So all these, apart from, of course, Clean Hydrogen Partnership related to aviation, is more about storage, more about infrastructures, but the groups work closely together in order to find synergies and common paths. That's again from the Clean Hydrogen Partnership. And very briefly also, just to be complete, the same, but for all TRL, for the whole range of TRLs, also for the air traffic management program, the CESAR 3, something similar, of course, is going on in the US. All these are complemented by what we call collaborative program, and I give you here a snapshot. These are biannual programs that we draft the technical program, and then we discuss it with member states, all European member states, in fact, all associated countries to the program, not only the European member states, so basically from many others beyond Europe. And then within a process of 9 months, we finalize a work program where all participants, industry, academia, and research laboratories can apply. Just to give you a brief look, that goes for the work program 2021-2022, 170 million euro, and then we start from destination 3 with priorities on sustainable aviation fuels, different pathways, and the certifications. On destination 5, more on technologies and policy, low TRL compared to the clean aviation one, with emphasis on non-CO2 emissions, manufacturing integration, digital technologies, and policy-oriented. Destination 6 on safety, so we support also EASA, and at the end, the last part, the dedicated programs related to EASA. So to arrive here, of course, it has been a long path. We have been funding projects related to climate neutrality and electrification for more than 20 years. So my mind goes back, of course, to the 3 main ones in the past, 3 big lighthouse projects, was POA, MOET, and Actuation 2015. And then in Clean Sky 1 and Clean Sky 2, the continuation of these projects took But even 10 years ago, I recall when we drafted the first work program on electrification, we had Pipistrel with a team, and they delivered, as you very well know, most of you, an excellent platform. Another representative example is the Distributive project, where a lot of work is done on propulsive fuselage and fundamental studies and concept analysis for different configurations. There's a Bauhaus, Luftfahrt, and the team. Enable H2, recently with, again, distributive propulsion and aircraft electrical technologies, as well as all the obstacles and the kind of mission critical, but also I get the word out of here now, but the obstacles for the introduction of liquid hydrogen in aviation. Many different studies and case studies, but I guess also this one was presented the first day or the second day here in ICAS on different configurations, many different configurations for liquid hydrogen and also tanks. The IMOTE project, another good example, where kind of in-depth analysis of hybrid power propulsion and multidisciplinary optimization. Footprint, I think it will be presented tomorrow, so I don't want to say too much about it, but again, on 20-seat regional electric aircraft, where different configurations and different conceptual studies have been performed. H3PS, or high scalability hybrid powertrains, and assumed on superconducting motors and rotors. What I want you to take away from this presentation today is that the program is fully open for international collaboration. If you are not sure if your country is not involved in this, then you all have to type is Horizon Europe Association Agreement. But most countries have signed an association agreement with the European Union. And out of the budget of 53 billion euro, a lot of budget is available for aviation research, not only from Clean Aviation, CESAR, Clean Hydrogen and the collaborative program, but also many other peripheral programs, as said earlier. So we are very happy, again, for opportunities for collaboration, including international one. And of course, we're extremely happy that this is aligned with industrial activities not only at European level, but also international level. That's all I had to say today. Thank you very much for your attention.
Thank you, Michael. So we will take some questions.
It deviates from the spirit of technical presentation, but I hope it was useful to some of you at least.
It was wonderful to see the big picture.
Yeah.
Really appreciate that. All right, any questions?
Yeah, I have a question about the recent summer that we've had with all the, especially in Europe, a lot of fires, and there's been a certain political pressure. And I would like to ask what you've noticed from the European Union, whether you've noticed some political pressure in terms of cutting aerospace. For example, France was saying of banning regional flights and only using trains. So maybe you could comment what there has been, kind of what you've seen from the European Council.
Of course, every member state is allowed to take whatever action they want, and of course we've seen these actions from France and the Netherlands. But the union policy goes beyond this. Is a kind of a more holistic approach, which is agreed by all member states. So. These are more operational issues, but here in the work program, in the research program, there's a kind of different mindset. There is an agreement from all member states. So, in fact, the process of creating all these technical documents and work programs is a kind of a 1 or 2 year process, and all member states participate and agree upon all these.
All right. Any other questions? Well, I think we'll just say thank you, Michael.
Thank you.
Thank you, everyone, for the session. Really appreciate your attendance and great questions. Stay safe and healthy. See you tomorrow.